Hello again, and welcome to my second presentation, which focuses on Newton's law of universal gravitation, with particular emphasis on the International Space Station, and includes one of my favorite videos right at the end. There are quite a few equations in what follows, but bear with me. After all, where would physics be without maths? Newton's law of universal gravitation says that the force of gravitational attraction between two masses is directly proportional to the size or magnitude of the two masses, in this case m1 and m2, and inversely proportional to the square of their distance apart, r. It is an inverse square law, and we can move from a proportionality to an equation by introducing a constant of proportionality, big G. In this case, big G is known as the gravitational constant, and we see a value indicated there. The equation has a negative sign, which indicates that the force is attractive, but we'll very often neglect that negative sign because we know implicitly that gravity is an attractive force. And of course, there is a force of gravitational attraction between the Earth and the Moon, between the Sun and the Earth, and indeed between me and the cup of coffee on the table in front of me. Now, you may not yet have looked at the topic of circular motion, but you will. In circular motion, you explore centripetal acceleration and centripetal force. Both of these act towards the center of the rotating system. In this case, the centripetal acceleration towards the center of the Earth is given by v squared over r for the satellite in orbit around the Earth, and the centripetal force, think F equals ma, it's m times v squared over r. Note the symbols that we'll be using and that we'll use SI units in all calculations. Also, r is the radius of the satellite orbit. It's measured from the center of the Earth and not from the surface of the Earth. The centripetal force is never some separate force, some imaginary force, some force that exists on its own. No, it is, in this case, the gravitational force. So let's equate the two, which is what we do in equation 1. And with a little bit of algebraic jiggery-pokery, we move quickly to equation 2. And we get v squared equals g times big M over r. For the satellite in orbit, generally speaking, speed is total distance traveled over total time taken. So the total distance traveled in one orbit is the circumference, 2 pi r. The time is the period for one orbit, big T. So v equals 2 pi r over t. Square things and we get equation 3. Now, equation 2, v squared equals equation 3, v squared equals. Let's equate the two and we get the equation at the top of the page here. Let's make t squared the subject of the equation and we get equation 4. Now here, t squared is directly proportional to r cubed because after all, 4 pi squared is a constant, big G is a constant, big M is a constant. The mass of the Earth doesn't change much from day to day. Okay, there may be a bit of debris raining on the Earth from space, but that's an insignificant change in mass compared with the whole mass of the Earth. So t squared equals k times r cubed. K is that constant, 4 pi squared over g times m, which of course is Kepler's third law. Now, Newton's brilliant insights explained Kepler's third law, which until then had been a purely empirical relationship. The International Space Station, the ISS, can we calculate its period of orbit, t? Well, can we do it? Yes, we can, in the immortal words of Bob the Builder. The mean height of the ISS above the surface of the Earth in October 2019 was about 416 kilometers. And yes, this value varies because of atmospheric drag. Even up there, the atmosphere is thin and tenuous, but there is still a drag acting, which over time, over months, would significantly reduce the height of the orbit. And so periodically, when a supply vessel goes up carrying provisions and or astronauts, it needs to be given a boost to bring it up to a higher orbit. Okay, we've got the radius of the Earth, the mass of the Earth. I've got the radius of orbit, which of course is measured from the center of the Earth. I've restated equation 4. And what I would like you to do now is to try and find a value of t for yourself. Put the values in, do the calculation, and see if you can find a value. And I'm going to ask you just to pause the video and see if you can do that calculation. So let's pause and get your calculator out. And we should find a value similar to the one I've got here, about 93 minutes, which is close to the actual orbital period of the ISS. I think it'd be interesting for you to find out more about the ISS and even to look out for it passing across the night sky. The Heavens Above website is useful in this regard. The Heavens Above website looks like this and includes information on when to watch out for various satellites and lots of other information about astronomy. Do have a look at it, but of course there are other websites that do similar things. If you are interested in personal tuition, then please do contact me. You'll also find my FES Physics contact details at the very end of this video. But whatever you're doing, keep studying and get ahead of the game, ready for the new term. Keep working. And almost finally, you really must watch this video of the Canadian astronaut Chris Hadfield singing Space Oddity, his version of the David Bowie hit. It's a great video, one of my favorites. So thank you very much. I hope you enjoyed that and keep working.